Hello, everyone. I'm Chaoyang, postdoc work with Professor Ekinci in Mechanical Engineering Department at Boston University. Today, I will give a talk for the IEEE Sensor 2020 about my work, how to optimize a piezoresistive motion detection for ambient NEMS application. This work is supported by Aramco company and NSF. So I will, based on the outline shown in slide, talk about my work. First, I will give a brief introduction, and then I'll talk about give a detail of the experiment results, which includes what device I use, how I do the actuation and detection. And then I discuss the dummies techniques used in this work. And I also talk about what kind of parameter can influence this optimization. And then I will give the discussion how I select these parameters in terms of background minimization. And then I will show the experiment results of measurement of NEMS resonance. And finally, I will give a conclusion. So in this work, I mainly focus on NEMS device with integrated piezoresistive strain sensor. This strain sensor allows for transduction of a mechanical signal to electrical resistance. Most of these devices have been operating in vacuum or low temperature because they have a high quality factor. The reduction in quality factor in ambient environment makes the detection signal more susceptible to the parasitic effect. However, many applications, for example, the environment monitoring and biochemical detection, are in ambient air. So this is one of the motivation of this work. Another important aspect of this work is that eventually we will put our NEM device into the liquid medium and try to measure the mechanical property of our liquid medium in the future. So this work in ambient air is very useful for our future applications. So let's go to detail of my work. First, this slide shows what device used and how I do the actuation. The device used in this work is silicon nitride double-clamped beams on the high tension. So we thermally and deposit this usual metallic thin film on both ends of the beam for actuation and the detection purpose. We electrothermally actuate the beam based on the fact that the thermal expansion coefficient of the gold thin film and the silicon nitride is different. When the current pass through, the things is heated up and it bends towards the substrate. When the temperature oscillates periodically in a frequency close to a resonant frequency of NEM device, this NEM device can be effectively actuated. So here we show the first 5 actuation mode shape of this NEM device, because in the experimental way, the thermal energy dissipated on the beam has quadratically dependent on the current. So in the experimental way, use omega d over 2 to actuate the beams. Omega d here represents resonant frequency of NEM device. And then we talk, in this lecture, we talk about the detection mechanism. Because of this detection nanoresistor also fabricate on top of the double-clamped beam, when this NEM device is actuated, it definitely deform the detection nanoresistor, and eventually result in increase in length, decrease in area of cross-section, because resistance is function of length and area of cross-section. So you will change the resistance of this detection nanoresistor. If this beam, double-clamped beam is actuated, so the detection nanoresistor will gain the time-dependent resistance change, which have this kind of form: delta R multiplied cosine omega dt. If you apply a current through this detection nanoresistor, and you can measure the motional of this NEM device electrically. So this lecture shows the down mixing techniques. The reason for using this down mixing technique is that the metallic thin film and the nearby ground can be formed or parasitic capacitance, and any of a high frequency signal in the detection circuit will be cut off to reduce this parasitic effect. And what we did is Then we apply a current with different frequency from this omega d. In that case, if we measure the voltage at this point, and the measured signal will be effectively mixed down because these two cosine are mixed down to the delta omega in this case. And in general case, the delta R is much smaller than R. So that's the reason we use a balanced circuit to further improve the signal to background ratio. So what we did is that we fabricate another nanoresistor here, which has the same identical dimension. This nanoresistor is for nulling purpose. We use a bridge circuit here and apply the out of phase voltage to R1 and R2. If R1 and R2 are exactly same, the voltage at point A only measure the time-dependent resistance change delta R term. However, due to the fabrication imperfections, R1 and R2 are not exactly the same. So to further improve the signal to background ratio, what we did is that we add a variable attenuator at the bridge circuit, and then to tune the voltage applied onto R1 and make sure the voltage at point A had minimum background. Based on the Kirchhoff law, we can calculate the voltage at point A and describe as this equation, where RL here is input resistance of preamplifier. So in the experiment, we want to know how the attenuation can influence background. Here is our experiment result. In right-hand side, where black dot is the experiment result, and red curve is the fitted curve based on our circuit model. So you can see they well fitted by our circuit model. And based on this study, we can know that what attenuation we can use to have this high signal to background ratio, which means have a background minimization. So, and then this slide show the background minimization by selecting the mix down frequency. In other words, is that a down mixing technique used in balanced circuit. Here, as a summary, we can see we apply a out of phase voltage to the bridge circuit, and then at point A, the voltage can be an effective mix down to delta omega. So in the experiment, I'm looking at amplitude as a function of the delta omega, which means the mix down frequency and the sweeping frequency. Here, for example, 600 kilohertz for the mix down frequency, and we see there the peak. This peak is the resonant frequency of NEM device. Here we take the data and plot off resonance amplitude as a function of the mix down frequency and showing in right-hand side figure. So you can see as mix down frequency increase, the background decrease at the beginning and reach a plateau and then increase a little bit later. So based on this study, we can understand or we can get idea background minimization happen when the mix down frequency is 630 kilohertz. So once we know these optimized parameters, we try to use them to study how the bias and drive voltage influence the NEMS resonance. Here, this slide shows the response of the NEMS resonator to bias voltage in ambient air. Here, I'm looking at amplitude as function of frequency, amplitude and phase as function of frequency, which show in figure A and B. So from green to black represents the bias voltage increase. So you can see increase the bias voltage, increase the current in the detection circuit, and then result large amplitude. So here I plot a peak amplitude as function of our bias voltage, while the peak amplitude here is obtained after background reduction. So you can see the experiment data, black dot, it fits linearly by this red curve. The reason is that because the resonant signal of NEM device is linear proportion to the bias voltage. By the way, the fitted curve passed through the point 0, 0. You can see this agree with our experiment data. And this slide shows the response of NEMs to the drive voltages. Again, in this figure, I'm looking at amplitude and phase as function of frequency, which show figure A and B. From blue to black represent the drive voltage increase. You can see increase the drive voltage, increase the thermal energy dissipated on the NAND device and resulting in a large amplitude. So here I plot the peak amplitude as a function of drive frequency, where the peak amplitude is obtained after background reduction. So the black dot here is experiment data, and you can see it's was fitted quadratically by this red curve. The reason for that is that the thermal energy dissipated on the beam has a quadratic dependency of the drive voltages. So this, you can see they also agree with our experimental result. Better the phase curve passing through 0 point. Okay, lastly is our measurement for the high order mode in ambient air. Figure A and B show the amplitude as function of frequency for the second and third mode. This amplitude is obtained after background reduction. So the resonant frequency measured here for the second and third mode are 10.4 and 15.5 megahertz. It's almost 2 or 3 times our resonant frequency of NAND device, which is 5.2 megahertz. The reason is that because our double clamp beam is under highly tension, so this more like the strain. So that's the reason. So you can see this also agree with our experiment data result. So lastly is our conclusions. And there's a 2 take-home message. And the first one, then balanced circuits in our work can definitely help us to reduce some of a parasitic effect. Second, the selection of the mixed-down frequency affects the background level in our circuit. Here, I also want to mention, although this mixed-down frequency is much smaller than the drive and the detection frequency, there's still some parasitic coupling between the signal. Yep, this is all the information from this work. Thanks very much for watching my presentation. It's my pleasure to talk with you guys. Thanks again. Thanks very much.